Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So, I want you to imagine stepping outside tomorrow morning. You know, you got your coffee in hand.
Best time of the day.
Oh, absolutely. So you walk out onto your porch, you look up at the morning sky, and instead of our single familiar yellow sun just kind of rising in the east,
Right.
you see 5 massive burning spheres of plasma just right there in the sky.
That would definitely wake you up faster than the coffee.
Right. I mean, they'd be casting these multiple overlapping shadows on your lawn. You'd have different hues of orange and red and this stark, blinding white.
It sounds like a backdrop for a massive space opera or something.
Exactly, like something cooked up in a sci-fi writer's room.
Right.
But the crazy thing is, in our immediate cosmic neighborhood, this is actually an absolute ongoing reality.
Yeah, it really is. And I think, our daily experience, waking up to just one sun that makes its journey across the sky completely alone, it creates this massive ingrained psychological bias for us. We just naturally assume the rest of the universe operates on this exact same single sun blueprint.
Because that's all we know. But being a single star, like our sun, actually makes us the absolute weirdos of the galaxy, doesn't it?
We really are the odd ones out. I mean, the human experience is just incredibly localized. We project our solar system's orderly single anchor structure onto the rest of the cosmos.
Which makes sense, logically.
Sure it does. But the sheer volume of stars out there that are actively bound up in these complex gravitational relationships with other stars, it's staggering.
It's a crowded universe out there.
Oh, incredibly. The universe is a far more dynamic and chaotic and just crowded environment than a casual glance at our night sky would ever lead you to believe.
So today our mission is to basically dismantle that bias completely. We're going to map out the precise relationship statuses of the stars closest to us.
Which is such a fascinating project.
It really is. Astronomers at the University of Madrid have just completed this incredible definitive census of our local cosmic neighborhood. And they're combining, modern space telescope data with century-old catalogs.
And we are going to explore exactly who is paired up, who is flying solo, and why untangling these incredibly complex stellar relationships is so important.
Right, because it's essentially the ultimate prerequisite for one of the greatest quests in human history, which is finding a second Earth.
Exactly. I mean, if the ultimate goal is to find habitable planets, worlds where liquid water could exist and life might thrive, we first have to thoroughly understand the stars those planets might be orbiting.
You can't just blindly point a telescope and hope for the best.
No, you really can't. The only way to build that understanding is to know exactly what is happening in our own backyard. We cannot filter the noise of the deep universe if we do not even know who is living next door.
Okay, so let's start by defining that backyard.
Yeah.
Because we need a boundary, right? We can't just say nearby.
Right. In astronomy, nearby could mean a million light years.
Yeah, exactly. So the astronomers compiling this definitive map, they drew this highly specific mathematical bubble around our solar system. The boundary is set at exactly 10 parsecs away from the sun.
Extending in every single direction to form a perfect sphere.
Right. And for anyone doing the cosmic math at home, 10 parsecs translates to 32.6 light years.
Which is a very specific number.
It is. And inside this specific 10 parsec bubble, there are exactly 424 known stellar and substellar objects. But I mean, 32.6 light years feels strangely arbitrary.
It does sound random at first.
Yeah, because the Milky Way galaxy is over 100,000 light years across. So why draw the lines so close to home? Why 10 parsecs?
Well, it all comes down to this foundational concept in observational astronomy, which is completeness.
Completeness, meaning we know everything that's in there?
Exactly. The primary enemy of any astronomical survey is distance. The further out into the galaxy you look, the harder it becomes to visually resolve the fine details of a star system.
Like trying to see the details of a car from 10 miles away.
Precisely. It becomes intensely mathematically difficult to see whether a star has a companion hidden right next to it because it just gets lost in the blinding glare of the primary star.
I was thinking about this like a neighborhood watch program.
Oh, I like that. How so?
Well, it's incredibly easy to know exactly who lives on your own street, right? You see your neighbors taking out the trash, you recognize their cars, you know exactly who lives in which house.
Sure.
You might even have a pretty good read on the street behind yours. But if you try to figure out who is permanently crashing on the couch of a house, like 3 towns away,
you wouldn't have a clue.
Exactly. From where you're standing, it is completely impossible. You just cannot see through the structural noise of the intervening houses and the distance to know for sure.
That captures the structural problem perfectly. Expanding the bubble to, say, 50 or 100 parsecs would introduce a massive amount of uncertainty into the data.
We just start missing the cosmic couch surfers.
Exactly. We would start missing things. By strictly limiting the boundary to exactly 10 parsecs, astronomers can mathematically lower the probability of missing those starry companions that are hiding in the wings.
So it's about confidence in the data.
Oh, 100%. This constraint allows for a very high degree of statistical confidence. The map is considered complete. We know we haven't missed any hidden roommates.
Okay, but wait. That still doesn't quite add up for me.
Oh, why not?
Because we currently have telescopes operating in space that are sending back crystal clear, high-definition images of galaxies that are billions of light years away.
Oh, right, like James Webb and Hubble.
Yeah. We are literally looking back in time to the dawn of the universe. So if the optics exist to capture a galaxy on the edge of the observable universe, why is it mechanically so difficult to spot a single companion star that is just, say, 15 parsecs down the cosmic street?
That's a really great point.
Right. Why does the physics fall apart at such a relatively short distance?
Well, the distinction lies in what those telescopes are actually resolving. When you look at a galaxy billions of light years away, you are not resolving individual stars.
You're just seeing the whole thing at once.
Exactly. You are observing the combined massive glow of hundreds of billions of stars spread out over an unfathomably huge area. It's a massive smear of light.
Okay.
But when you look at a star system just 15 parsecs away, you are trying to resolve a tiny, specific point source of light.
You are looking for a single microscopic dot.
And that dot is unimaginably bright. I mean, stars are colossal nuclear fusion engines. They create a blinding amount of glare.
Right. They aren't just reflecting light, they are making it.
Exactly. So if a companion star is orbiting relatively close to a primary star, the light from the primary completely washes out the dimmer companion.
I see.
Think of it like trying to spot a firefly hovering 3 inches away from a stadium floodlight while you are standing 2 miles down the road.
Oh, wow. Yeah, the sheer volume of photons from the floodlight would just utterly destroy your ability to perceive the firefly.
Exactly. The firefly is completely swallowed by the visual noise.
So it's not a distance problem, it's a glare problem.
Precisely. This limitation is governed by something called angular resolution. No matter how perfectly polished your telescope mirror is, or how advanced your sensors are, light ultimately behaves as a wave.
Right.
So when light waves pass the edges of a telescope's aperture, they bend and spread out. This is a phenomenon called diffraction.
Diffraction, okay.
And this creates a tiny blur around every point of light on the sensor. If 2 stars are too close together in the sky, their diffraction blurs overlap.
And they just merge into a single blob of light.
Exactly. Keeping the census tightly constrained to 10 parsecs means the physical distance between the stars translates to a wide enough angle in our sky. It ensures the floodlight and the firefly appear far enough apart that our instruments can reliably separate them.
Okay, that arbitrary number makes total sense. It's literally the physical limit of knowing our data is pure.
Exactly.
Now, compiling a flawless map of 424 objects isn't something you do by just pointing a backyard telescope at the sky and taking notes, right?
Definitely not.
The data required to prove these objects exist, and more importantly, to prove they are actively interacting with each other, that must be monumental.
Oh, it's staggering. The census is the culmination of combining 2 of the most sophisticated, massive data sets ever compiled by humanity.
Wow, what are they?
The structural backbone of this map comes from the DR3 data release from the European Space Agency's Gaia telescope.
Gaia. I've heard of that one.
It's an incredible piece of technology. Gaia is a space observatory specifically designed for astrometry.
It's astrometry. That's the precise measurement of where things are.
Location, distance, and motion.
Yeah.
Exactly. Gaia is essentially building a highly dynamic, 3-dimensional map of the entire Milky Way galaxy.
That's ambitious.
Very. It measures the positions of over 1 billion stars with a level of precision that is honestly difficult to overstate. It can measure the width of a human hair from hundreds of miles away.
Seriously. That is insane.
It's phenomenal engineering. But positional data is really only half the puzzle.
Right, because just knowing where two stars are doesn't mean they are interacting.
Exactly. To know if stars are actually in a relationship, you need movement over time. That is where the researchers brought in the Washington Double Star Catalog.
Now, I was looking at the history of the Washington Double Star Catalog. It is fascinating because it isn't just a modern digital list. It represents decades, even centuries, of human observation.
It really is a historical treasure. It's the world's principal database of visual double stars. It actually contains historical observations dating all the way back to the 19th century.
Wow. So people with early telescopes sketching things out.
Basically, yeah. And that historical data is combined with decades of modern radial velocity measurements.
Radial velocity being how fast a star is moving along our line of sight, like either toward us or away from us.
You've got it perfectly. By fusing Gaia's ultra-precise 3D positioning with the deep historical motion data from the Washington Catalog, astronomers could trace the exact trajectories of these objects over time.
So they can see the actual dance.
Yes. They could definitively prove which stars were locked in a gravitational embrace and which were just optical illusions.
Optical illusions, like stars that look close together from Earth, but are actually separated by vast distances in deep space.
Exactly. We call those optical binaries. They just happen to line up perfectly from our vantage point, but they have nothing to do with each other.
Okay, so the 10-parsec bubble is set, the pristine data is gathered, and all the false positives, those optical illusions, are filtered out. Let's dig into the actual census results.
Let's do it.
Who is actually paired up in our neighborhood? Out of the 424 objects inside this bubble, 215 of them are bound up in multiple star systems.
Which means over half the population is coupled up.
Literally more than half the neighborhood is in a relationship. And they aren't just in simple pairs either.
No, it gets much more complicated.
These 215 objects are distributed across 92 distinct multiple star systems. And the structural breakdown of these systems is shockingly diverse.
It really runs the gamut.
Right. So there are 68 classic double star systems, binaries. But then there are 19 triple star systems.
3 stars all dancing together.
Yeah. And then there are 3 quadruple systems. And perhaps the most mind-bending of all, there are 2 incredibly rare quintuple star systems.
5 stars.
5 separate stars, all gravitationally bound to each other, existing as a single cohesive unit.
Visualizing a system with 5 massive bodies of burning plasma is challenging because our brains just naturally default to our own solar system model.
Right. I was reading about the structural dynamics of these quintuple systems, and my mind went straight to how they even organize themselves without crashing.
It's a delicate balance.
Because you can't just have 5 stars orbiting a single point like a cosmic merry-go-round, right?
Yeah.
The n-body problem in physics dictates that throwing 5 massive objects into a random clump just results in pure chaos.
Absolute chaos. They would violently fling each other around.
Yeah. They completely destabilize the orbits until the system either collapsed inward on itself or forcefully ejected stars out into deep space.
Exactly. So to survive for billions of years, gravity forces them into highly organized, compartmentalized layers.
What's the term for that?
It's called a hierarchical structure. They do not orbit a central star. They orbit a shared center of mass.
A shared center?
Yes, known as a barycenter. And they do this through nested levels of organization.
Nested levels? It reminds me of the intricate gears inside a mechanical Swiss watch.
Oh, that's a brilliant comparison.
Because you don't have 5 gears all grinding against the exact same central axle. You have a massive, slow-moving outer gear. And then, nested inside that, you have smaller assemblies spinning independently.
Right.
And within those, even tighter, faster-moving parts.
The watch analogy perfectly captures the mechanics. So in a quintuple system, you might have 2 stars in a very tight binary orbit circling each other rapidly.
Like the ticking second hand.
Exactly. Then, a massive distance away, but still within the exact same system, you have another tight binary pair.
Okay, 2 separate pairs.
Yes, and those 2 separate binary pairs will then orbit each other.
Wait, the pairs orbit each other?
Yes. The gravitational center of pair A orbits the gravitational center of pair B. They treat the other pair almost as if it were a single extra heavy star.
Orbiting pairs of orbiting pairs. That is dizzying. And the 5th star?
The fifth star is often situated in an incredibly wide orbit, just slowly circling the entire inner quadruple structure from a massive distance.
Like the outer casing of the watch.
Exactly. Moving at a glacial pace compared to the rapid ticking of the inner binaries. And the sheer vastness of space between these hierarchical levels is actually what preserves the system.
Because they're kept far enough apart to not interfere.
Right. The gravitational forces at play locally within a tight binary are intense, but because the next structural level is located so far away, that competing gravitational pull is diluted.
Ah, I see. They establish a long-term stable resonance. But, okay, if I am a planet in one of these quadruple or quintuple systems, what does my existence even look like? With all these competing gravitational wells, do planets even survive in these environments, or are they just shredded into asteroid belts?
It's a rough neighborhood for a planet. The gravitational environment is incredibly hostile unless they settle into very specific, mathematically safe zones.
Safe zones? Like where?
Well, a planet can survive if it is in an extremely tight, close orbit around just one of the individual stars. In that scenario, it effectively ignores the distant pull of the other stars in the system.
It just hugs its parent star really tightly?
Exactly. Or, on the flip side, a planet can exist in a circumbinary orbit.
Circumbinary, meaning orbiting the whole thing.
Right, orbiting incredibly far away from the entire complex, treating the inner mess of stars as a single gravitational point.
Okay, so way inside or way outside?
Exactly. Anything in the middle ground, the spaces between the interacting stars, that is a dynamically unstable death zone.
A death zone?
A planet caught there would eventually be ejected from the system entirely or pulled into a catastrophic collision course with a star.
So no middle ground. The mechanics are just awe-inspiring. But, beyond just mapping the structures, the census revealed this really striking mathematical rule about who actually ends up in these complex relationships.
Oh, yes. The relationship between mass and multiplicity.
Right. There is a definitive, unyielding link between a star's mass and its relationship status.
It's fascinating.
If a star is categorized as a heavyweight, meaning it possesses more than half the mass of our sun, it has a massive 41% chance of being paired up with at least one companion.
Almost a coin flip. Mass dictates cosmic sociability. The heavier the star, the more likely it is to exist in a complex system.
But then the complete opposite is true for the lightweights. We're talking about objects under 0.1 solar masses.
Right, the red dwarfs and the brown dwarfs.
Yeah. For these lightweights, the fraction of being found in a multi-star system absolutely plummets. It drops all the way down to just 9%. They actively seem to avoid entanglements.
And that massive statistical drop-off from 41% down to 9% is not just a quirk of our local neighborhood.
No.
No. It provides crucial forensic evidence for one of the most intense ongoing debates in stellar astrophysics, the mystery of how substellar objects actually form in the first place.
Interesting, because I look at gravity like a form of cosmic social currency.
Social currency.
Yeah. Like the heavier you are, the more gravitational charisma you possess. You can attract other bodies, lock them into orbit, and basically hold on to them through the chaotic early days of star formation.
That's a great way to visualize it. The heavyweights clearly have that currency. They travel in packs.
Right. But it begs the question regarding these tiny red and brown dwarfs. Are they born alone because they simply lack the gravitational mass to attract a partner? Or is something more violent happening?
More violent.
Could they have been born into a larger group dynamic and then violently kicked out?
Well, you are outlining the two leading models for brown dwarf formation right there.
Oh.
Yep. But to understand the debate, you first have to look at what a brown dwarf actually is. It is the ultimate cosmic tweener.
A tweener. Not a planet, not a star.
Exactly. It is significantly more massive than a gas giant planet like Jupiter, but it does not have quite enough mass to generate the core pressure needed to ignite sustained nuclear fusion of hydrogen.
So it never caught fire.
Right. It glows faintly from the residual heat of its formation, but it is not a true hydrogen-burning star.
Just kind of smoldering.
Exactly. Now, consider the birthplace of stars. They form in these massive freezing clouds of interstellar gas and dust called molecular clouds.
Okay, giant freezing clouds.
Right. And as these clouds collapse under their own gravity, they do not form a single smooth sphere. They fragment into dozens, hundreds, or even thousands of dense clumps.
So it's messy.
Very messy. This fragmentation is why stars naturally form in clusters, and this perfectly explains the 41% pairing rate of the heavyweights.
Because they form together out of the same dense, chaotic clump of material.
Exactly, and they simply never left each other's gravitational grip. They were born as a bound pack.
So where do the lightweights, the brown dwarfs, fit into that chaotic cloud?
Well, the first theory is the ejection hypothesis.
Ejection. Getting kicked out.
Right. It proposes that brown dwarfs start forming just like their massive siblings within these dense, crowded fragments of the molecular cloud.
Okay.
But because they are forming in an environment alongside much heavier, much faster-growing stars, the gravitational tug-of-war is incredibly violent.
So there are the runts of the litter getting pushed around.
Basically. Before the brown dwarf can gather enough gas to reach the critical mass for fusion, the heavier stars gravitationally bully it.
They bully it.
Through complex orbital interactions, the massive stars slingshot the tiny brown dwarf, violently ejecting it from the multi-star system entirely.
So they were part of the complex watch gears for just this brief chaotic moment,
Right.
but got stripped out and flung into the void.
Exactly. Under the ejection hypothesis, their isolation is the result of a violent eviction.
Brutal. What's the other theory?
The competing theory argues for isolated formation.
Which means they were alone from the start.
Right. This model suggests that the immense molecular cloud also contains very tiny, isolated, extremely low-mass pockets of gas on the fringes.
So away from the dense, chaotic center.
Yes. A brown dwarf forms from one of these tiny pockets entirely on its own. It was born alone in a quiet, isolated environment with barely enough material to scrape by.
Just scraping together whatever gas it could find. The census data showing a 9% pairing rate feels like a massive clue here.
It strongly limits the theoretical models. I mean, the fact that 91% of these lightweights are flying solo in our 10-parsec bubble heavily suggests that whatever mechanism creates them, whether it is violent ejection or isolated formation, is incredibly efficient at leaving them alone.
It's so cool how this works. The local census essentially acts as a forensic time machine. It allows astrophysicists to test the mathematical models of star formation from billions of years ago against the reality of our current neighborhood.
It really grounds the abstract theories in hard data.
And that perfectly transitions into the actual mechanics of how these surviving relationships operate. Because we know the mass rules, we know the structures, but the orbital physics within these systems are pushed to absolute logic-defying extreme.
Oh, the extremes are mind-boggling.
Right. The time it takes for these stars to complete one full lap around each other, their orbital period varies wildly depending on the system.
Immensely.
On one extreme, you have tightly bound pairs that whip completely around each other in a matter of days. I mean, imagine a planetary year lasting 72 hours.
You'd have a birthday twice a week.
Right. But then on the far opposite extreme, you have stars so widely separated that a single orbit takes tens of millions of years.
And dealing with those extremely wide binaries presents one of the most massive observational challenges in all of astronomy.
I bet. I mean, the tight orbits are easy to comprehend. It is like a couple holding hands 24/7.
You can clearly see they're together.
Exactly. They are inseparable. A single glance tells you they are bound together. But a wide binary with an orbit taking 20 million years. That is like a long-distance relationship maintained by a single text message sent once every millennium.
That's hilarious, but scientifically accurate.
If I point a telescope at a wide binary, the physical distance between them is staggering. They don't look gravitationally bound. They just look like two passing strangers who happen to be drifting through the exact same cosmic zip code.
Well, when an orbital period is measured in the tens of millions of years, the curvature of that orbit is virtually flat from the perspective of human observation.
Because we're only seeing a tiny slice of time.
Exactly. You are not watching a circle being drawn, you are looking at a straight line.
Wait, if the orbit takes tens of millions of years, human history hasn't been around long enough to watch even a microscopic fraction of a percent of it happen.
Not even close.
I mean, Galileo first pointed a telescope at the sky a mere 400 years ago. If we cannot wait millions of years to watch the orbit actually curve, how can we possibly calculate the binding energy?
It's a great question.
How do astronomers definitively prove they are actually tethered together by gravity and not just two random stars drifting past each other in the dark?
The detective work required to prove a wide binary is bound relies on a concept called common proper motion, and that's combined with highly precise kinetic energy calculation.
Okay, break that down for me. Common proper motion.
Since we cannot observe the orbital curve, we measure velocity and direction. Imagine two airplanes flying across the ocean.
Okay, two planes.
They are separated by miles, but they are flying in the exact same direction, at the exact same speed. Even if you cannot see a physical tether between them, it is mathematically highly improbable that two unrelated planes just happen to perfectly match speed and heading over the middle of the Atlantic.
They'd have to be flying in formation.
Exactly. They're part of the same group. The same principle applies to stars.
So they're moving together across the sky.
Yes. Gaia measures the proper motion of these stars, which is how fast and in what direction they are physically moving across the backdrop of the galaxy.
Oh, I see.
If two widely separated stars share a common proper motion, it is a massive red flag that they are associated.
A red flag in a good way.
Right. But association is not the same as being gravitationally bound. They could still be slowly drifting apart. To prove the tether actually exists, astronomers have to calculate the system's total energy balance.
Wait, how do you weigh a star you can't touch? You need to know their mass to know their gravity, right?
Exactly, and we do that through spectroscopy. By analyzing the spectrum of light the star emits, we can determine its temperature, its composition, and ultimately, its mass.
Light reveals mass. That's so elegant.
It is. So once we know the mass of both stars, we know exactly how much gravitational pull they exert on each other. Then we look at the historical radial velocity measurements from the Washington Double Star Catalog
To see the push and pull.
to determine their exact three-dimensional velocity relative to each other.
So we figure out exactly how heavy they are and exactly how fast they are moving apart from one another.
Yes. Because every mass generates an escape velocity.
Escape velocity, like a rocket trying to leave Earth. The speed required for an object to break free of its gravitational pull forever.
Precisely. The researchers painstakingly calculate the kinetic energy of their relative motion against the potential energy of their combined gravity.
So speed versus gravity.
Exactly. If their relative speed is even a fraction lower than the escape velocity at that specific distance, the math is unequivocal. They cannot escape.
Wow.
Even if it takes 10 million years for the gravitational tether to haul them back around, they are permanently bound. The math proves a physical reality that time itself moves too slowly for us to witness.
I love that. I absolutely love how the math reveals the invisible mechanics of the universe. It's almost poetic.
It's what makes astrophysics so rewarding.
But as incredibly fascinating as a million-year orbit or a quintuple star system is, these stellar companions are not universally celebrated by all astronomers, are they?
Oh, definitely not.
In fact, if you talk to a planetary scientist, companion stars are often described as a massive, absolute nuisance.
A total headache.
Right. When we are trying to do one of the most important things in modern science, hunt for habitable exoplanets, these multi-star systems become an observational nightmare.
A hidden companion star is literally the last thing you want to uncover in a target system when you are searching for a second Earth.
Why is that? I mean, the sheer physics of multiple massive bodies interacting, does it just completely ruin the delicate data required for exoplanet detection?
It completely ruins it. To understand why the data is so fragile, we have to look at the primary methods used to find exoplanets.
Okay, because we aren't just looking through a telescope and seeing a planet.
No, planets do not generate their own visible light. They only reflect the light of their host star. And next to the blinding glare of a star, a rocky planet like Earth is virtually invisible.
The firefly and the floodlight again.
Exactly. So instead of looking for the planet itself, we look for the gravitational influence the planet exerts on its host star.
Looking for the footprint instead of the person.
Right. And the most established method for doing this is radial velocity.
We touched on radial velocity with the catalog data. It measures the star moving toward or away from us.
When applied to planet hunting, radial velocity requires staggering, almost incomprehensible precision.
Because the planet is so small.
Yes. Here is the physical mechanism. Gravity is a two-way street. When a planet orbits a star, it doesn't just circle a stationary object pinned to the fabric of space. The planet has mass, so its gravity tugs back on the star.
So the star is moving too.
Yes. Both the star and the planet orbit that shared center of mass, the barycenter. But because the star is exponentially heavier than the planet, the barycenter is usually located deep inside the star itself.
It's like a seesaw, where a massive adult is sitting right next to the fulcrum, and a toddler is all the way out on the other end.
That's a perfect visual.
The adult barely moves, but they do shift just a little bit to balance it out.
Exactly. So the star doesn't trace a wide orbital circle. It just wobbles back and forth around that internal barycenter.
It wobbles.
As the star wobbles toward Earth, the light waves it emits get slightly compressed, shifting toward the blue end of the spectrum.
Blue shift.
Yes. And as it wobbles away, the light waves stretch out, shifting toward the red end.
Red shift. Like a police siren changing pitch as it drives past you.
The exact same principle, but with light instead of sound. Astronomers measure these microscopic color shifts to prove an unseen planet is pulling on the star.
The scale of this measurement is what just completely blows my mind. I mean, looking for a massive Jupiter-sized planet is one thing. That's a big toddler on the seesaw.
Right, it creates a big wobble.
But looking for a small, rocky, potentially habitable Earth-like planet using radial velocity, that's like trying to listen to a mouse's heartbeat through a stethoscope.
It's incredibly faint.
The signal is so delicate. A planet the mass of Earth barely moves our sun at all. It induces a wobble of maybe 9 centimeters per second.
Which is what, the speed of a slow crawl?
Yeah, a slow crawl.
Yeah.
Trying to measure a star moving at 9 centimeters per second from 30 light years away is an absolute triumph of human engineering.
It's a miracle we can do it at all.
But if that star has a companion star is like someone standing right next to you while you have that stethoscope pressed to the mouse, and they just start blasting a heavy metal concert out of a stadium speaker.
The heavy metal concert completely drowns out the mouse.
Every time.
The gravitational tug-of-war inflicted by an entire other star, even a small red dwarf, completely warps the radial velocity readings.
Because the star is being yanked around so violently by the stellar companion that you could never, ever detect the gentle centimeter per second tug of an Earth-sized planet hiding in the same system.
The data is entirely polluted by gravitational noise.
So radial velocity is completely off the table for these multi-star systems. We just can't use it.
It's useless there.
But the future of exoplanet hunting is moving beyond just detecting shadows and wobbles, isn't it?
Oh, very much so.
We are entering an era where astronomers want to actually see the planets. The next generation of space observatories is currently being designed and funded as we speak.
It's a very exciting time.
The heavy hitters coming down the pipeline are NASA's Habitable Worlds Observatory, known as HWO, and the European Space Agency's Larger Interferometer for Exoplanets, or LIFE.
These observatories represent the absolute pinnacle of astronomical ambition.
They really do. Their primary mission is monumental. They are specifically designed to directly image an Earth analog.
Which means they want to physically capture the photons bouncing off a rocky, habitable zone planet.
Direct imaging. No more inferring a planet exists through gravity or shadows. Just pointing a massive camera into space, blocking out the star, and taking a picture of a blue dot.
Exactly. And the mechanism they use to block the star is called a coronagraph.
A coronagraph? How does that work?
It is essentially a highly engineered physical mask inside the telescope that perfectly eclipses the primary star's light. By blocking the blinding floodlight, it allows the incredibly faint light from any orbiting planets to become visible.
It's like putting your thumb over the sun so you can see a bird flying past.
That's a great everyday example. However, the stakes for this kind of observation are almost unquantifiable.
Because of the cost.
Telescope time for observatories of this magnitude is one of the most expensive and fiercely contested resources in human history. We're talking about billions of dollars of engineering and decades of planning.
Think about the tax dollars and the sheer human effort poured into a project like HWO. I mean, as a listener, your tax dollars are likely helping fund this pursuit right now. The pressure to point that multi-billion-dollar lens at the correct target is immense.
It is, because to get a direct image of an Earth analog, these observatories cannot just snap a quick photo like a smartphone.
It's not a point and shoot.
No. The target planet is so dim, billions of times dimmer than the star, that the telescope will need to lock on and stare at a promising candidate system for weeks at a time.
Weeks?
It takes weeks of constant observation to gather enough individual photons to slowly build a single workable image of the planet.
Weeks of staring at one single spot in the sky. So if you dedicate 3 weeks of multi-billion-dollar telescope time to a star system, and you unknowingly target a star that has a hidden, widely separated companion in the background,
it would be an unmitigated disaster for the observation.
the whole thing is ruined.
Oh, absolutely. If there is a hidden companion star sitting just outside the edge of the coronagraph's mask, the background light noise, the glare from that companion, would completely wash out the delicate, sparse photons arriving from the exoplanet.
Just a wash of white noise.
And the resulting data would be utterly ruined. The researchers would have wasted the most valuable scientific time off the planet staring at light pollution.
Oh man, that hurts to even think about. But this brings the entire purpose of the cosmic census into brilliant, sharp focus, doesn't it?
It does.
This massive effort to map 424 objects in our 10-parsec bubble is not just about cataloging stars for the sake of having a list.
No, it's highly practical.
It is essentially a highly vetted do-not-call list for these future mega telescopes.
That's the perfect term for it.
It is a precise target map that tells HWO and life exactly where it is mathematically safe to look.
It is the ultimate filtering mechanism. By painstakingly identifying the 215 bound objects and cataloging the 92 multiple star systems, the researchers have instantly identified which stars have a high probability of polluting direct imaging data.
With either light noise or chaotic gravity.
Exactly. The telescope operators can confidently cross those systems off the primary target list.
The paradox of this research is just brilliant to me. I mean, we spent all this incredible effort combining decades of the Washington double star catalog with the cutting-edge astrometry of Gaia, calculating complex binding energies for million-year orbits, and mapping 424 objects down to their precise coordinates, largely so we know exactly which ones to ignore.
I know, it sounds counterintuitive. But in the realm of high-stakes astronomy, eliminating false positives is just as vital as identifying a prime target.
You have to clear the brush.
Right. If you are searching for a needle in a massive cosmic haystack, the most efficient strategy you can employ is to aggressively and systematically burn away all the hay that you know definitively does not contain a needle.
Burn the hay.
By clearing the board of these multi-star systems, we can focus all our precious, limited observational resources on the quiet, stable, isolated stars.
The loners. The stars drifting through the galaxy completely unattached.
Stars exactly like our sun.
Let's pull all these threads together to see the complete picture of our cosmic neighborhood. Because we started by drawing a mathematical boundary, a perfect 32.6 light-year sphere around our solar system, just to ensure absolute completeness.
And inside that 10-parsec neighborhood, we analyzed 424 objects.
And we discovered that our human bias is completely wrong. Roughly half the neighborhood is actually paired up.
It's a busy street.
It is. We learned that mass dictates relationship status, right? With massive stars thriving in complex double, triple, and even intricately layered quintuple systems.
The Swiss watches of the galaxy.
Exactly. While the tiny brown dwarfs remain isolated, likely due to violent ejections early in their formation.
The outcasts.
We explored the dizzying extremes of orbital physics, from pairs whipping around each other in days to wide binaries tethered together across tens of millions of years by invisible, calculatingly precise gravitational bonds.
And ultimately, we uncovered why this definitive map is so critical.
Right. It clears the literal and figurative noise. It provides our next-generation telescopes like HWO and LIFE with a clean, pristine roadmap to hunt for a second Earth by actively avoiding the chaotic, heavy metal concerts of multiple star systems.
It is a remarkable achievement that fundamentally changes our perception of our local environment. It transforms a mysterious, chaotic void into a meticulously mapped, understood terrain.
We now know the layout of the neighborhood.
We do.
It is the foundation for everything that comes next. And as we wrap up this exploration, I want to leave you with a final lingering thought to mull over.
Okay.
When we look up at our lone, companionless sun, it is really easy to feel a sense of profound isolation. We feel like we're just drifting through the dark, empty space of the Milky Way entirely by ourselves, disconnected from the cosmic dance happening all around us.
It can feel very lonely.
But given everything we've just unpacked, given how violently companion stars warp the gravitational environment, given how they flood a solar system with blinding light noise, and given how inherently hostile a multi-star system is to the delicate formation of a planet, think about what that implies for our very existence.
The silence is the point.
If human ingenuity ever does pinpoint a perfect, tranquil alternative Earth nearby, a world where life has had the billions of years of uninterrupted quiet necessary to evolve, it will almost certainly be orbiting a star just as lonely as ours.
The visual spectacle of a multi-star system with 5 suns in the sky might be breathtaking from a distance.
It would be stunning.
But that sheer chaos is fundamentally incompatible with the fragile, steady development of a habitable world.
So perhaps our sun's isolation isn't some tragic cosmic anomaly. It isn't something to feel lonely or adrift about. Maybe being a lone star is the precise, absolute necessary prerequisite for life.
A requirement, not a bug.
The quiet solitude of our single sun sky isn't a flaw in our solar system's design. It is the exact, tranquil reason we are here, sitting on this porch, able to look up at the sky and wonder about the universe in the first place.